The integration of advanced electromechanical systems presents a formidable challenge for Tesla, particularly concerning the incorporation of ultralight actuators and multidirectional visual sensors. This complexity notably influences both the production timeline and overall efficiency. To meet the ambitious price point of below $25,000 for the Optimus robot, cost optimization becomes essential for Tesla. Accomplishing this objective necessitates the rapid and precise manufacturing of every component involved in the production process. Moreover, Tesla encounters regulatory challenges in demonstrating that Optimus can operate safely alongside humans across diverse environments. Comprehensive safety testing is imperative to preclude any setbacks within the company's robotics strategy. In addition, China's export controls on rare earth magnets, driven by national security considerations, have a direct impact on Tesla's supply chain and production stability for the Optimus robot. This situation has potentially led to increased costs within the supply chain. In a competitive landscape, XPeng's humanoid robot Iron exemplifies advanced features, including a significant range of motion and powerful artificial intelligence capabilities, effectively positioning it as a substantial competitor to Tesla's Optimus. Elon Musk's ambitious production targets for Optimus encompass scaling operations to 1 million units per year. However, these goals face notable challenges associated with supply chain management and intense market competition from both Chinese and domestic rivals. The Optimus V3 incorporates a redesigned, lighter carbon fiber frame that enhances mobility. Nevertheless, this innovative design may lead to a considerable increase in production costs when compared to previous models, representing a significant technological advancement. Furthermore, the new robot features enhanced dexterity, characterized by hands equipped with 11 degrees of freedom. This improvement enables the execution of intricate tasks that earlier iterations could not perform, albeit with a potential initial rise in production costs. Tesla's mass production strategy could substantially reduce costs, facilitating the realization of the desired price point through the advantages of economies of scale and advanced manufacturing techniques. This approach is critical for achieving competitive pricing. In terms of revenue generation, Tesla's decision to offer robots for sale or lease can enhance financial performance through subscription services. This strategy not only democratizes access to advanced technology but also mitigates price competition, appealing to a diverse range of customer segments. Additionally, vertical integration empowers Tesla to manage production costs effectively by controlling essential components. This approach significantly reduces expenses in comparison to competitors who depend on external suppliers for critical parts, such as batteries and chips. Achieving economies of scale via mass production could enable Tesla to competitively price the Optimus V3, drawing parallels to the market transformation observed with smartphones. This capability could serve to stimulate widespread adoption of the technology. By manufacturing core components in-house, such as batteries and AI chips, Tesla streamlines its operations and reduces costs compared to rivals that rely on third-party suppliers. This vertical integration is vital for sustaining competitive pricing. Leveraging real-world data from its extensive vehicle fleet accelerates Tesla's AI training processes for Optimus, rendering them more cost-effective and efficient than the conventional methods employed by other robotics firms. Finally, Tesla's internal testing of Optimus robots within its factories facilitates immediate feedback and rapid iteration. This strategy effectively avoids the costly delays and inefficiencies encountered by competitors that depend on external testing protocols. And of stability and mobility features in Tesla's Optimus robot has progressed at an unprecedented pace, successfully overcoming challenges that have historically taken other organizations years to address. This rapid advancement not only highlights Tesla's innovative capabilities but also showcases the remarkable potential inherent in contemporary artificial intelligence. In addition to these advancements, the competition within the realm of humanoid robotics is intensifying. Various models are emerging, each demonstrating impressive mobility and diverse capabilities. With an aim to distinguish itself, Tesla seeks to leverage superior technology and rapid development, echoing its strategic approach observed in the electric vehicle sector. Initially, human-like dexterity in robotics faced skepticism. However, this feature enables the Optimus robot to execute a wide array of tasks. Unlike conventional industrial robots, which are confined to specific functions, such versatility is crucial for applications within household environments. Significantly, Optimus possesses the ability to adjust its grip force automatically, representing a marked improvement over earlier robotic models that struggled with accommodating varying weights and delicate objects. This enhancement not only boosts operational efficiency but also expands the potential applications of the robot. The landscape of competition is evolving rapidly, as startups swiftly align with Tesla's technological advancements in dexterity and functionality. This democratization of technology signifies a transformative shift within the robotics market, where barriers to entry are diminishing. Furthermore, the introduction of large language models enables Optimus to better understand and respond to human commands, marking a pivotal milestone in the domain of household robotics. This capability significantly enhances user interaction and improves task execution efficiency. Tesla's distinctive manufacturing capabilities, exemplified by their innovative gigapress technology, afford the company a considerable advantage in the mass production of humanoid robots. This unique expertise may empower Tesla to scale its operations more rapidly than its competitors. The significance of solid-state batteries lies in their lightweight composition and superior energy density, effectively addressing the critical limitations of current battery technologies utilized in humanoid robots. This technological advancement holds the potential to considerably enhance operational durations for robotic systems. Moreover, the transition to solid-state batteries not only stands to improve safety by mitigating fire risks but also aims to elevate the overall performance of humanoid robots. Enhanced charging times could further amplify operational effectiveness, making these robots more reliable. Elon Musk's design philosophy emphasizes simplicity and efficiency, a vision closely aligned with the objectives of integrating solid-state batteries into the Optimus robot. This approach could streamline production processes, ultimately contributing to greater efficiency. Should Tesla successfully implement solid-state batteries within its robots, it may pave the way for advanced battery technologies and AI-driven energy optimization. This advancement would signify a substantial leap forward beyond conventional systems. The advantages offered by solid-state batteries, such as higher energy density and reduced weight, render robots like Optimus more agile and efficient. This characteristic is particularly critical for executing complex tasks effectively. A lighter Optimus robot stands to move more swiftly and operate for extended periods without necessitating recharging, thereby enhancing its practical utility across diverse applications. This increased efficiency directly influences the robot's overall performance. Moreover, Tesla's robust battery supply chain facilitates reduced production costs and enhances operational flexibility. This strategic advantage enables the company to manufacture solid-state batteries internally, thereby leading to significant competitive benefits. Lastly, the deep integration of solid-state batteries into the robot's design can significantly enhance performance while conserving space for other vital components. This optimization further bolsters the robot's functionality and efficiency, particularly in executing complex tasks. New walking style of Optimus Gen 3.5 closely emulates human biomechanics, thereby facilitating smoother movement and minimizing energy expenditure. This pioneering approach distinctly sets it apart from earlier robotic iterations. Furthermore, the coordinated arm swings exhibited by Gen 3.5 enhance both balance and fluidity in motion, thereby fostering a more human-like interaction style. This particular design choice significantly augments the robot's functionality across diverse operational environments. In addition, Tesla's implementation of auto-simulation technology has permitted the robot to engage in extensive virtual training, effectively compressing thousands of hours of learning into mere days. This advanced technology substantially bolsters the robot's adaptability to real-world conditions. Moreover, the robot's optimized foot landing technique minimizes impact stress, showcasing a sophisticated understanding of biomechanics. Such innovation holds the potential to enhance the efficiency of robots in executing a variety of tasks. However, despite these impressive motion capabilities, there remain pertinent questions regarding scalability and the consistency of performance across mass-produced units. Manufacturing variances could significantly influence the qualitative aspects of the robot's walking capabilities. Transitioning to real-world challenges, factors such as wear and computational demands are pivotal in evaluating the long-term viability of the robot. Achieving effective responses in unpredictable environments continues to represent a considerable hurdle. The design of the charging stations features a streamlined architecture that facilitates docking while the robots remain standing, thereby enhancing operational efficiency and reducing wear on mechanical components. This innovation signifies a noteworthy advancement in the domain of robotic charging. Tesla's charging framework underscores a focus on simplicity and modularity, optimizing spatial utilization within industrial settings. This innovative design may enable the concurrent charging of numerous robots, effectively mitigating overheating concerns. Moreover, the incorporation of real-time fleet management software will prove essential in optimizing charging and maintenance schedules. Tesla's objective is to ensure the efficient utilization of each robot, thereby enhancing their operational longevity. The layout of Tesla's facilities closely resembles military barracks, suggesting potential applications in high-security environments. This strategic approach aligns with their recent recruitment efforts for specialized roles in sensitive operational areas. Furthermore, Tesla's design integrates advanced cooling systems to effectively manage heat generation. This feature is critical for sustaining optimal performance levels in robots that operate under high thermal conditions. Operational efficiency is further maximized through the implementation of a 3-shift rotation for robots. This strategic approach enables continuous operation while significantly reducing real estate and downtime costs. Learning curve principle in manufacturing indicates that as production scales up, the cost per unit significantly declines. Tesla's experience in electric vehicle production exemplifies this principle. Leveraging existing technology from its electric vehicle division gives Tesla a substantial edge in producing Optimus. This advantage stems from the ability to reuse and enhance various components and systems. To widen accessibility, introducing a subscription or leasing model for Optimus could attract a more extensive customer base. This approach mirrors successful strategies seen in the software industry. Designed for industrial applications, Optimus Pro can efficiently handle tasks such as loading and assembling goods. Its pricing, ranging from $60,000 to $75,000, mirrors substantial labor cost savings. In contrast, Optimus Lite aims at middle-class families by focusing on affordable household tasks. Priced between $15,000 and $20,000, it streamlines daily chores without the need for heavy lifting. Addressing the increasing need in healthcare, Optimus Care offers support for elder care. With a projected retail price of $25,000 to $30,000, it presents significant savings compared to traditional live-in care. By setting a high price point, Tesla effectively mitigates overwhelming demand, which helps avoid supply chain complications and customer dissatisfaction. This pricing strategy reflects lessons learned from previous product launches. Focusing on specific customers, such as enterprises and research institutions, ensures that early adopters supply valuable data. This information is vital for refining software and improving the product. A high entry price also allows Tesla to gauge market readiness for humanoid robots. It provides an avenue to recuperate R&D expenses while laying a financial groundwork for future advancements. Enhancing Optimus capabilities, the integration of the FSD processor boosts reaction speed and real-time data processing, which is essential for efficient task execution. This technological advancement is rare among current commercial humanoid robots. Tesla adopts a learn-by-doing approach with Optimus 2.5 by deploying it for real tasks in factories. This feedback-driven method refines both AI and hardware, aiding the early establishment of mass production. In a significant move, Tesla is not merely developing prototypes, it is actively preparing for the mass production of Optimus units. This strategy highlights Tesla's leadership in robotics execution speed and readiness for commercialization. Elon Musk asserts that Gen 3 robots will achieve human-like agility, highlighting speed, precision, and flexibility as critical traits needed for dynamic environments. This perspective shifts focus from sheer strength. Realizing agility in robotics entails the integration of force, vision, and inertial sensors for precise motion prediction.
This presents a considerable technical challenge for humanoid robots like Optimus.
Tesla's robust AI infrastructure, including the Dojo supercomputer, is crucial for training the neural networks of the Optimus robot. It enhances the robot's capability to interact and adapt to diverse environments. The creation of new materials and actuator systems is vital for optimizing Optimus Gen 3's performance across various human-centered fields, including healthcare and manufacturing. Tesla's manufacturing strategy prioritizes simultaneous development of products and production lines, fostering faster iteration and improved efficiency for Optimus robots. By employing shared components and software-defined manufacturing, Tesla aims to lower the cost of Optimus, potentially achieving a price point below $20,000. Optimus Gen 3 operates at a velocity of 6.8 miles per hour, rendering it suitable for integration within industrial environments without causing disruptions to ongoing operations. This capability exemplifies Tesla's substantial investments in advancing technology and mobility. In contrast to other humanoid robots primarily focused on agility, Tesla places a strong emphasis on the optimization of Optimus's hands. This prioritization enables the robot to execute intricate tasks, including cooking and cleaning, with remarkable efficiency. Elon Musk envisions Optimus Gen 3 as an invaluable asset across multiple sectors, particularly healthcare, where it could play a supportive role in surgical procedures. This perspective underscores the robot's versatility, extending its potential applications beyond mere household functions. The deployment of innovative battery technology featuring 4,680 cells empowers Optimus Gen 3 to function continuously for up to 10 hours without the necessity of recharging. This represents a significant enhancement compared to previous robotic models. Optimus Gen 3 employs sophisticated artificial intelligence systems to learn from real-world experiences, mirroring the learning processes of humans. This advanced capability facilitates intelligent interactions with its surrounding environment. To refine Optimus Gen 3's performance, Tesla gathers human motion data that allows the robot to replicate actions with exceptional precision. This training process involves employees utilizing motion capture suits to meticulously record their movements. The robotic hand of Optimus Gen 3 is engineered for both flexibility and precision, thereby enabling it to execute delicate tasks with a degree of dexterity and smoothness akin to that of humans. Such advancements mark a significant progression from earlier robotic models. Incorporating tactile sensors and miniaturized actuators, Optimus Gen 3 effectively addresses the limitations encountered by robots in the past, enhancing their capacity to perform tasks that require sensitivity and responsive feedback. This technological development permits safe handling of fragile objects. Elon Musk foresees a future in which robots like Optimus Gen 3 render work optional, fundamentally transforming the dynamics of labor and daily life for human beings. Such projections prompt critical considerations concerning the evolving nature of employment. The integration of Optimus Gen 3 into manufacturing facilities has the potential to considerably enhance productivity by automating intricate and repetitive tasks, encompassing roles in assembly and quality inspection. Designed to undertake hazardous tasks that may jeopardize human safety, Optimus Gen 3 is adept at operating heavy machinery in perilous environments. This safety-centric approach contributes significantly to fostering a healthier workforce. Tesla has set an ambitious objective of producing millions of Optimus Gen 3 robots on an annual basis, aiming for widespread application across diverse industries ranging from healthcare to manufacturing. This aspiration signifies Tesla's unwavering commitment to pioneering innovation. Recent advancements in artificial intelligence and sensor technology empower Optimus Gen 3 to function proficiently in real-world settings, adapting to human gestures while executing precise tasks. This capability represents a transformative shift in how we engage with technology. Elon Musk underscores the importance of accessibility concerning Optimus Gen 3, asserting that it should be available to all individuals, not solely the affluent. This initiative aims to democratize robotic assistance, thereby benefiting a wider demographic. Ultimately, the mission of Tesla's Optimus Gen 3 is to liberate individuals from the constraints of repetitive labor, empowering them to concentrate on more enriching aspects of life. This paradigm shift harbors the potential for fostering a more balanced approach to work and personal well-being. Tesla Bot Gen 3 emphasizes practical household tasks, moving away from flashy performances to assist with cleaning and everyday chores. This shift signifies a notable change in robotic design philosophy. Equipped with advanced sensors and a multi-angle camera system, the Tesla Bot navigates and comprehends home environments in real time, significantly enhancing its cleaning efficiency. In contrast to traditional humanoid robots, Tesla Bot learns and adapts to a family's cleaning habits over time, ensuring that it executes tasks at optimal times and in ways tailored to each household. Optimus utilizes computer vision and reinforcement learning, allowing it to effectively differentiate between normal behaviors and potential threats. This capability is essential for its role in enhancing home security. The robot's ability to adjust and learn from real-world scenarios distinguishes it from others, which typically rely on basic motion and facial recognition. This learning process empowers Optimus to make independent decisions. Elon Musk envisions a future where Optimus generates income for users by working in diverse roles, free from the constraints faced by human workers. This potential has the capacity to transform the labor market and economy. Small businesses stand to benefit from autonomous robots, which could lower labor costs and increase operational efficiency, enabling them to function with minimal human oversight. This transition could overhaul service industries. The rise of humanoid robots will create new job opportunities in areas such as robot training, maintenance, and human-machine interface design, fostering a new workforce that reflects historical trends in technological advancement. Tesla's goal to implement Optimus in factories aims to demonstrate its economic feasibility, illustrating how robots can boost productivity and profitability for businesses. This initiative underscores the potential of human-robot collaboration. Significant design modifications, including a revamped aerodynamic front and a lighter chassis, enhance the energy efficiency and driving range of the 2026 Tesla Semi. The integration of advanced sensors and cameras in the 2026 Tesla Semi is vital for enabling full self-driving capabilities, addressing driver fatigue and significantly improving safety on the roads. Tesla's new Giga Semi